So today's lab is acid-base, and we're looking at the last part of your lab packet, page 101. Objective number 1 asks you to identify the normal range of pH for the blood and the body fluids. So do you remember what the pH of blood is? Yeah, 7.35 to 7.45. So if we look at the pH in the different body compartments, as far as if we look at, for example, blood in the veins versus blood in the arteries, which one would you expect to be, even though it's within the normal range, which would you expect to be slightly lower, more acidic? Yeah, why do you say veins? Exactly. And we know that a culminating statement after being in this class, if you remember anything at all, right? What is it? Right. CO2 makes acid. So anytime CO2 is building up in the system, it's creating acidic conditions, right? So that's why when we want to check somebody's, oxygen levels, we want to, and carbon dioxide levels, we want to look at arterial blood, because that's the fresh blood that we need to see if the lungs are working and doing their job of blowing off CO2 and bringing in good oxygen. So the normal pH is 7.35 to 7.45, but venous blood is about 7.35, arterial blood is about 7.4, and the intracellular fluid is 7. So we have a balance of electrolytes in there, so we don't see any net charge or pH change, but it's a little bit lower. So when we talk about anything that is lower than 7.35, let's say the pH is 7.3, that's still above 7, right? So if we're looking at a generic pH scale, we would say, oh, that's alkaline. But we call it acidosis in the body because it's below the normal range. So if you see 7.30, that's considered an acidosis, even though it's above 7. We call it physiological acidosis because it's acidosis relative to what the normal pH for blood is supposed to be. So alkalosis is anything above what then? Right, 7.45 is alkalosis, less than 7.35 we say is acidosis. And there's two different types of acidosis and alkalosis that we're going to talk about today. One is caused by lung function, so we call that a respiratory or acidosis or respiratory alkalosis. If it's caused by something outside the lungs, something's going on in the body that's changing pH, not breathing, not lung function, then we call that a metabolic acidosis or alkalosis. And you can see in the flow chart that I gave you, there's different reasons and causes for each of those. So looking at how our body accommodates and adjusts for these slight pH changes, like if I, am exercising hard, I'm going to end up with a little bit of extra CO2 on board, right, from working muscles, metabolizing glucose to keep those muscles working. Our body accommodates that in a couple of different ways. Because pH is our chemical reactions in our body, our enzymes are very pH sensitive. So if we don't regulate pH, it's going to affect metabolism and denature proteins and cause a whole host of problems. So it is regulated by a couple of different things, by buffer systems, by the kidneys, which we're going to talk about in lecture primarily on Wednesday, and then also by the medulla. Remember, the medulla oblongata has chemoreceptors for pH, right? And if pH is dropping due to CO2, the medulla stimulates the respiratory system, right, the diaphragm, and increases the ventilation rate. So those are three ways that the body controls pH. The main one we're going to talk about in this lab are the buffer systems. There's chemicals, 3 different buffer systems chemically that we can use to either soak up excess hydrogen ion or release excess hydrogen ion, depending what the conditions of the body are. When would these chemical reactions want to release hydrogen ion? What type of pH would these buffer systems release? Tatum? Yes, when we have a high pH, that's an alkaline scenario, right? So we want to release hydrogen ion to bind up that alkaline whatever is being released and bind that and bring that back down to within normal range. So we've got the bicarbonate buffer system. We talked about that. Remember, carbon dioxide travels in the blood mostly as bicarbonate, and that transfer of CO2 right? Forming carbonic acid and then releasing bicarbonate ion. Remember, the red blood cells have that special enzyme where that conversion occurs. Do you remember the name of the enzyme in the red blood cells? Carbonic anhydrase. Okay, so that's what makes bicarbonate ion, and that again, that reaction in the red blood cells of breaking down or forming carbonic acid is the most large-scale buffer system that the body has. So the bicarbonate buffer system is the most popular buffer system in the body as far as being able to respond within seconds of a pH change. That bicarbonate buffer system kicks into gear. So if you go to the next page, page 102, there's the reaction for the bicarbonate buffer system. So this happens in red blood cells. So carbonic acid is here. That's a weak acid. And what that means is that it breaks apart into its ions. So we can see this is a double-sided arrow, right? So that means this equation can go back and forth. But what this means is it tends to break up into ions just a little bit, and the rest stay as carbonic acid. So we call that a weak acid because a lot of it stays as a complete acid, you know, bound together and does not release as many ions or dissociate. Something that's a strong acid completely dissociates into ions, and it's going to release a lot of hydrogen ion into the system. Like hydrochloric acid is an example of a strong acid. So it's going to change pH a lot more than carbonic acid would, because carbonic acid moves to the right less frequently than it does moving to the left. So it stays together. So this is the most popular one, and we see this in the extracellular fluid. And this is one of the questions on your matching worksheet, is which buffer system is most common in the extracellular fluid. That's the bicarbonate buffer system. The protein buffer system, where do we see a lot of protein in the body? Within cells, inside cells, because that's the job of some cells, is to make proteins, right? So this is a very popular buffer inside of our cells, and it's also popular somewhere else. Where else do we see a lot of proteins? We're talking about it right now in the urinary system. In the plasma, yeah, those plasma proteins. So in the blood and inside cells is where the protein buffer system is most popular or most widely used. And then we have the phosphate buffer system, and this is active in the kidneys and also inside cells as well. So phosphate buffer system is popular in the nephron when we're forming urine and inside cells. So the key one in the extracellular fluid is the bicarbonate buffer system, and it's the most widespread of the buffer systems. So it's again, we're taking these, for example, proteins. If I look at a protein, I don't know if you guys remember chemistry at all. Do you remember the term Zwitter ion at all of a protein? Yay, should we talk about it? What'd you say? Oh, you are. Okay, so it's fresh in your mind. Yeah. So what it basically means is a protein, when it's dissolved in solution, it has a carboxyl end, it has a COOH minus end, and it has an NH3 plus end. Do you remember that? Right? So I think it's NH3 plus. It's been a while. Yeah. If it was NH4, I was trying to remember, but it's NH3 plus. So either side, the plus side, the NH3 plus side, could soak up what? What would be in the environment that would change pH? Would it attract positive or negative? The NH3 plus side would attract negative. So the negatively charged ions that can change pH are bicarbonate ion or hydroxide ion. So those are basic things, right? So that side can bind up excess of that. And the other side, the COOH minus, can bind up positively charged ions. And what's the number one positively charged ion that influences pH? It's a direct measurement of its concentration. Hydrogen ion. Okay, so that's how those proteins work. It just depends, it just kind of shifts the charge to bind those ions depending on which is in excess. And then phosphate comes from phosphoric acid. So again, if you look at that reaction here, it just depends what direction we're moving the reaction if we need to bind up excess hydrogen ion or release it. So obviously if we're releasing it, we're driving the reaction to the right, and if we need to bind it up, we drive the reaction to the left. So these act as buffers, changing the pH depending on what the levels are. Okay, so if we go back to our objectives here, those are the different buffer systems. And if we look at the lab values that tell us acidosis or respiratory acidosis, metabolic acidosis, let's look at this flow chart here. And the first thing we look at to determine is it alkalosis or acidosis, step number one is just look at what is the pH. So the pH is going to tell us what path we're going down. Do you guys need a copy of this? Okay, yeah, come on up here. I have a copy of the matching, I've got the case studies and the flow chart. So I wanted to make sure everybody had all their materials today. So if it's greater than 7.45, we know that's an alkalosis, but now we have to figure out what kind, and that's where the challenge is. Is it respiratory? Is it metabolic? And acidosis, same thing, respiratory or metabolic. All right, so the first thing is respiratory. The respiratory system can only affect the PCO2. Would you agree with that? That's really the only thing the respiratory system can do is blow off carbon dioxide. Everybody agree with that, right? So if the PCO2 is high or low, then something's wrong with the lungs. Would you agree with that? So then we know it's respiratory based. So if I look at the pH, and let's say in this case the pH is low, let's just say it's less than 7.35, what do we know about CO2 again? CO2 makes acid. So what would I expect the PCO2 to be if someone had a respiratory acidosis? It would be high, right? CO2 makes acid. So the more CO2 I have in that blood, the more carbonic acid and hydrogen ion is going to be released. So that would be a respiratory acidosis. I look at the PCO2. Let's say the PCO2 is normal, well then I know it's not respiratory. Now I look at what's metabolic, which means I can only control the bicarbonate ion. The kidneys can either reabsorb bicarbonate or not reabsorb bicarbonate when it enters the nephron. So if I want to determine if it's a metabolic, then the bicarbonate ion is going to be off. So acidosis means I have a low bicarbonate ion because this is a negatively charged ion, so therefore it binds up excess hydrogen ion. So think of bicarbonate ion as acting like a base in the system. So if the base values are low, then that's obviously acidosis, right? And if my base is high, if bicarbonate is high here, that would be an alkalosis. So the first thing you look at is what is the pH? Then you determine, is the low or high pH caused by abnormal PCO2 or abnormal bicarbonate? Once we've determined that, then we have to say, is the body trying to accommodate by the other system? So let's say we say it's respiratory, is the metabolic system trying to compensate? So if I have a low PCO2 making me alkalotic, then the bicarbonate system is going to try to fix that by lowering the bicarbonate ion in the blood. Because if I have low bicarbonate, that creates more acidic conditions, doesn't it? So that's going to raise my pH. Lower my pH. Lower. And if it's uncompensated, that means like the kidneys are non-functional, then I'm going to have a normal bicarbonate ion. So we need to go through the different situations here and think about what would cause that. So let's look at respiratory alkalosis. If a person is hyperventilating because of anxiety, pain, exhaustion, whatever, mental illness, that's going to cause excess loss of what? Right, excess loss of CO2. So I don't have enough CO2, and that's going to, remember CO2 makes acid, and if I don't have enough of that, I'm not going to make acid, so I'm going to have a higher pH. That would be respiratory based. High bicarbonate ion would be from kind of strange situations here, would be taking too many antacids, sodium bicarbonate is a common, compound found in antacids. So if I took too many of those, I might end up in having a metabolic alkalosis. And then prolonged vomiting, if I lose hydrogen ion, what happens to pH if hydrogen ion goes down in the system? It goes up, right? So I have alkalosis from prolonged vomiting because I'm losing hydrogen ion. So those are metabolic reasons, right? These are outside the lungs. And the only way I can determine if it's metabolic is I have to see, is this abnormal? So acidosis, high PCO2 causing respiratory acidosis. To compensate for that, the kidneys are going to reabsorb bicarbonate ion and keep that in the system because that's going to bind up that excess acid from the high PCO2. What would cause that high is anything that slows respirations down, right? Because you're building up carbon dioxide and you're not blowing it off from the lungs. So if it's a respiratory acidosis, it means we're not blowing it off enough. Respiratory rate is too low. So anything that lowers the respiratory rate, like too much pain medication, anytime you put someone on a narcotic medicine on a drip or like a PCA pump, have you heard of those where you press the button, it gives a little dose of medicine for people that have extreme pain? Well, we put them on a special sensor to measure their PCO2 in their exhale and their respiratory rate, because even oxycodone, if I give somebody too much oxycodone, that can slow their breathing down to the point that they die from that. And that's what heroin addicts are dying from, right, is suppressing their respiratory rate. So what do we give them to counteract that? Everybody knows the answer to this one in every class If someone has a reduced respiratory rate because of too much heroin, what does their buddy give them? Sometimes right there at the party. This is becoming another street drug. What is it? Yeah, exactly. Narcan. I knew somebody would know it. Yeah, and that's, becoming just as popular as the heroin is now, because now you can wake up and continue to party. So it's really it's a catch-22, isn't it? I mean, we're using it in the ambulances to save lives, but at the same time, it's just carrying on, that irresponsible abuse of drugs. So anyway, but it's it's good when it's an accidental overdose, obviously, due to increased pain meds and things like that. Okay, lung disease. So if a person has advanced emphysema, asthma, anything that prevents the respiratory membrane from not blowing off and, getting rid of that CO2 from the blood to the lungs is going to cause respiratory acidosis. So anytime we have things building up in the blood outside of the lungs, so if we have a metabolic acidosis, that can be from diarrhea. In the large intestine is bicarbonate ion that's meant to be reabsorbed back to the blood. But if that stool leaves the body prematurely in the form of diarrhea, the body's lost that bicarbonate ion. So loss of bicarbonate ion causes an acidosis. Because remember, think of bicarbonate, starts with a B, think of it as a base. Okay, so when you see bicarbonate, you're thinking base. Diabetic ketoacidosis, remember, if the sugar is stuck in the blood and it can't get into the cells because insulin is not sufficient, then the cells are starving and they start eating fat around them, fat and protein, and that causes ketoacids or ketones to form. And as a result of that those keto acids are going to lower the pH. If we are using our muscles, so someone's doing an Ironman, and they've been going for a really long time and their body is not conditioned for that, they can end up with a metabolic acidosis, because what's building up in their muscles? Lactic acid. Seizures can do that as well. The body's certainly not primed to be seizing for half an hour, and that does happen. Some people have uncontrolled seizures, and that's really something we have to look out for in those patients, is an acidosis because of that extreme prolonged metabolic activity, and they're not breathing very well during that either. Okay, so again, just kind of in a summary at the bottom of the flow chart here, if it's a respiratory acidosis or alkalosis, something is going on with the breathing. So think of the lungs or the respiratory rate. What are they doing in their breathing that might be throwing off the pH? And metabolic, it's something outside the lungs. So it's pretty straightforward. All right, so let's go look at the worksheet first with the matching, and then we'll go from there and see I'll give you time to work on your case study. So number 1, pH. Okay, measure of hydrogen ion concentration. Substances that minimize shift in pH. They minimize it. It's a generic term for the 3 we mentioned. Buffers, right, C. That's COOH and NH2. It's actually NH3. You could change the 3, that to a 3. But yeah, protein buffer. That is letter H. Thank you. A substance that accepts hydrogen ion. E, a base. Phosphoric acid and phosphate ion are all part of J, phosphate buffer system. Substance that donates hydrogen ion. B, B, an acid. Carbonic acid and bicarbonate are part of the A, bicarbonate buffer system. Solution with a pH less than 7. D, acid. Solution with a pH of 7. L, neutral solution. Blood pH less than 7.35. What do we call that when it's blood pH? Acidosis. Number 11, blood with 7.35 to 7.45. G, normal homeostasis. Blood pH above 7.45. I, alkalosis. Most important and responsive extracellular buffer. Which one was that? A, yep. Intracellular and blood buffer. H, correct. And intracellular and urine buffer. J, the phosphate. I would highlight, underline these. I remember these being, oh, you're not taking a lab exam this semester. We've got kind of a really weird lab schedule. Normally this is on our last lab exam. I don't know why. It must have just been because of Thanksgiving or something. What? Is that what you think it is? Because we still had a lab exam and lab that week, so I'm not quite sure what happened. Anyway, normally these would be on the lab exam, and for the online students, it's important because that will be on their lab exam. So, okay, so looking at the different disorders, so now we'll kind of pull these different things together. So if a patient has emphysema, so impaired ability to move carbon dioxide across that respiratory membrane, what's that going to cause? Yes, respiratory acidosis, because carbon dioxide can't blow off. So anytime you're looking at these things, you're either thinking, is this going to cause a problem with bicarbonate ion, lactic acid, hydrogen ion, or anything with CO2, with the lungs? Okay, prolonged vomiting of stomach contents only. So you're losing hydrogen ion. What would that be? Metabolic alkalosis, right, letter D. Patient overdoses on aspirin, and aspirin is acetylsalicylic acid. Yep, metabolic acidosis, because you're ingesting a lot of acidic content with those aspirin. Overdose of antacid. Someone else besides Grace? D, metabolic alkalosis. Good. Number 5, patient with prolonged diarrhea. What does a person lose with diarrhea? What ion? Bicarbonate. So what do you think? We lose bicarbonate, metabolic acidosis. Good, because you're losing base, right? Bicarbonate is a base, so if we're losing base, that makes us acidotic. Hyperventilating from anxiety. Respiratory alkalosis, good, because they're losing too much CO2 in that hyperventilating. Patient with severe uncorrected diabetes mellitus. So that's where they've shifted over to those keto acids, right? A, metabolic acidosis. Person compensating for hypoxia while backpacking at Pikes Peak. So they're compensating, they're breathing, they're having a really hard time getting oxygen, so they're breathing really hard and fast. Yep, respiratory alkalosis. So they're trying to make up for that. And that's what that altitude sickness can become for some people. Or it can just cause, nausea, dizziness, vomiting, dehydration. It's bad news. I know some people that had it. We have relatives in Colorado. Number 9, patient with overdose of drugs that depress the control center. What did you say that was? Yes, respiratory acidosis, because they're not breathing. The control center is the respiratory control center, which is what part of the brain? Medulla, yep. So CNS depression, coma, stupor, drowsiness, those are the symptoms. What did I say you should look for when you see a patient, other than blood sugar? If you come in and they're really lethargic and sleepy, what should you be thinking? Yeah, high PCO2. So when we're acidotic, whether it's metabolic or respiratory, they just act like they're so sleepy and drugged. Then get a blood gas, if you think it's respiratory, right? And you don't get the blood gas unless you're going into medical school here. That's probably not your immediate path. Maybe some of you will be there, but that's what you're thinking. That's when you tell their respiratory therapist to say, do we need a blood gas on this person? So A and B, right, for that. And then nervousness, hyperexcitability, possible seizures, that's a sign of alkalosis, so C and D. Okay, so the next part now is to look at the case studies that are posted here and work through those on your own with a partner. So I should say with a partner. It's kind of putting everything together now. You've got specific gravity information, you've got glucose in the urine, so you've got urine information that's going to tell you some things. What do we assume right away if we see sugar in the urine? Diabetes. Yep. And you're going to look at, but the 2 primary things, what's the first thing you're going to look at in all these case studies? Number 1, using the flow chart, pH, and then you're going to look at PCO2 or the bicarbonate ion. Which one is off, right? Whichever one is off, that's the cause. If bicarbonate ion is off, and that matches, and I should clarify, I'm going to show you one quick thing here before you get started. So if this is whatever this is, so let's go on the right side. Let's say it's low. Okay, let's say it's an acidosis. Then we look at the PCO2. Does the PCO2 value, does that make sense for the acidosis situation? If it's a high PCO2, does that cause acidosis? Yes. What if I look at the PCO2 and it's really low? That means that the lungs are compensating, because there's situations, ideally, in a healthy body that if one of these is off, if the bicarbonate is off because the kidneys, say, aren't working, or there's some metabolic ketoacidosis going on with a diabetic, then the lungs are going to try to fix it by changing the breathing rate. So we call that a compensation. So if I've got a metabolic acidosis, so we've got acid conditions, what is the body going to do? What are the lungs going to try to accomplish? What is the medulla going to stimulate the diaphragm and external intercostals to do? If we have a low pH, they want to do what? I'm sorry? Well, if we've got a low pH, because of a lot of keto acids, if we slow the respiratory rate, wouldn't that make it even more acidic? So what do the lungs want to do? What? Yeah, increase the respiratory rate. So what we see is rapid, deep breathing in people that are trying to compensate for like a diabetic ketoacidosis. We call it Kussmaul's respirations. It's K-U-S-S. You don't have to write it down, M-A-U-L''S. You'll read about that in the nursing program or in your area where you're going. But that's the way the lungs are compensating for that. And if it's a respiratory thing, we're going to see a change in bicarbonate ion, right? You're going to see a change in bicarbonate ion potentially in the plasma if we do an arterial blood gas. So we're looking for compensation. So pay attention to that as you do your case study. And if you have any questions, I'll come around and help you. But before you leave, I want you to turn in your paper and I'll quick give you a score on it.